Hello, welcome to the video. And this lesson, we're looking at 6.3, where we're going to find exponential functions. So by the end of this particular section, we are going to be able to graph a exponential function. What that means is one of the variables is going to be the exponent. And it just so happens that this one will be x. And here is the general formula for most exponential functions. It's going to look like y is equal to a times it by b raised to the x power. Now, it does get a little bit more complex than that, but as a general rule of thumb, that is a good starting point for our graph. And we'll look at what a exponential function looks like using this form here. But for starters, we're going to look at tables to see if, in fact, a table is going to represent either a linear function or a exponential function. So we've talked about tables that represent a linear function. Anytime that a table is going to represent a linear function, it is going to have something that is called a common difference, which means you subtract everything the same by the same value with respect to y. When it comes to an exponential function, you're still going to have something in common, but it's going to be what is called a common ratio. So if you look at example A, looking at x, everything looks like it's consistent, so it's 0, 1, 2, 3. For B, it's 0, 1, 2, 3. I'm good with x, everything's consistent with x. What I want to look at is the values for y. So for y, it's 2, 4, 6, and 8. So if it has a common difference, that means the subtraction is the same. So if I took 4 subtracted by 2, I get 2. 6 subtracted by 4, I get 2. 8 subtracted by 6, I get 2. That has a common difference. This does not have a common ratio. Common ratio would be like if I took 4 divided by 2, I get 2. And if it had a common ratio, it would have to be 6 divided by 4 would be 2, which doesn't, it's not the case. So since this one has a common difference, example A is linear. Looking at B, if I try to look at common difference, 8 minus 4 is 4, but 16 minus 8 is 8, and 32 minus 16 is 16. So there's no common difference, but let's say there's a common ratio. What is 8 divided by 4? 2. What is 16 divided by 8? 2. What's 32 divided by 16? 2. This one has a common ratio. The ratio in this case is 2, so this means that example B is exponential. So A is linear, B is exponential. If it has neither a common difference or a common ratio, then it's neither linear nor exponential. It's something else. Here they want us to evaluate an exponential equation with a given value of x. So here this is my exponential equation, and they're saying that they want you to evaluate it when x is 3. So essentially you got y is equal to -2 times it by 5, and it's raised to the third power. talking about order of operation, nothing changes. We got to take care of exponents first. So 5 to the third power is 125. So I got y is equal to negative 2 times it by 125. And that means that y is going to be equal to negative 250. For b, I got y is equal to 3, and it's going to be what? 0.5 raised to the negative 2 power. Negative 5 to the negative 2 power is 4. So now I got 3 times 4, which equals 12. Here, here are the examples of two types of exponential functions. This first one here, it's still y is equal to a times it by b raised to the x power. We talked about that in the beginning of the section. But what we want to take a look at is these are the types of graphs that we're going to look like when b is larger than 1. So b is always going to be a positive number. But what we're going to take a look at is that when b is larger than 1, when a is positive, my graph is going to curve from left to right upward. And when a is negative, when it goes from left to right, it's going to be kind of curved downward. When you look at the second graph over here, still the same general formula, but now B falls between 0 and 1. So it's a fraction between 0 and 1. Anytime that occurs when you're going from left to right, it's going to be kind of going downward. And this one here is going to be kind of going upward. What this is, and we'll kind of dive in a little bit more into it in 6.4. Anytime b is greater than 1, this is an example of exponential growth. It's more in tune when a is positive, but it's an indicator of exponential growth. And then when b is a fraction between 0 and 1 is an example of exponential decay. So, but again, we'll talk more about exponential growth and exponential decay in 6.4, but just to give you an idea of what that will kind of look like as we move forward. A is always going to be like your quote unquote y-intercept, and then it'll move upward from there, whether a is positive or whether a is negative, and we'll kind of get an idea of that. So in order to graph an exponential function, let's look at one like this. All right, all I really want you to do is I want you to graph it. I'm not that concerned about you describing domain and range. I'm not or being able to compare it. So just graph it. If I were to look at a graph, let's see here. Like this. So what I would advise you to do is, even though it's f of x, let's change it to y. So it's going to be y is equal to 4 times it by 2 raised to the x power. Every time until you become comfortable with graphing these, write out the general formula. Y is equal to a times it by b raised to the x power. Figure out what a is. A is 4, and b is 2. Since a is 4, the first thing you're going to do is you're going to try to find that y-intercept. It's going to be 0, comma, whatever a is. And since a is 4, I got 1, 2, 3, 4. I plot that point. For my value b, since b is greater than 1, it's an example of exponential growth. And it kind of will look like this. It won't cross the y-axis because remember, those terms will then be undefined. So that is the graph for that particular function. If we go into this one here, I got f of x is equal to negative 1/2 raised to the x power. So again, graph this. Again, all I'm really concerned about is you being able to graph it. So let's change it to y is equal to negative 1/2 raised to the x power. Again, let's write out general formula. A is right here. A is a negative 1, and B is 1/2. So just like the other graph, the y-intercept is going to be 0, comma, A, which is negative 1. So I plot that point right there. And because B is 1/2, that's a example of exponential decay. So with a being a negative number, it means it's going to kind of come up and it's going to look something kind of like this. And that's all I really want you to concentrate on, is be able to concentrate on how the graph would look for that particular situation. Now this one here creates a little bit more variables because they have the exponent is now x minus 3, and now this one is plus 2 on the outside, which means there is a particular shift in the graph. So how I want you to graph these types of situations is this, is let's imagine that there is no shifting of the graph. Let's take a look at, let's get rid of the minus 3 and let's get rid of the plus 2. So if I said y is equal to 4 times it by 2 raised to the x power, how would you graph that? So going back to this form, A is 4, B is 2. My y-intercept is 4, 1, 2, 3, 4. It's right here. And B being positive, it's an exponential growth. My graph would look something like this. This is what this graph would look like. Now, all you are going to do here is, all right, there was a change in x and there's also going to be a change in y. So this is where my change in x comes from, and this is where my change in y comes from. If you recall, we talked about shifting things with respect to h and k with absolute value. If you recall, we had the y is equal to a times by the absolute value of x minus h plus k. If you guys remember that, this was absolute value. And the h dealt with the shifting either right or left, depending on what my value of h was, and k was up or down, depending on the value of k. Well, this, when you have that shift, is going to be y is equal to a times it by b, and instead of it just being raised to the x power, it's going to be the x minus h power, and then you got a plus k. So this is the form that it would look like when you would have that particular shift. So looking at this, h in this particular example is 3 and k in this particular example is 2. So what's going to happen is from here, I'm going to move 2 to the right, 1, 2, and 3 up, 1, 2, 3. So this, I'll make it a different color. This red dot is now like my new y-intercept, essentially. So what happens is everything gets moved up 3. So 1, 2, 3. So essentially, you're just going to take this graph right here and move it to there. Now, what I would do is look at it this way, like, all right, this is what my graph is going to look like now with respect to the shift. And I put the dashed line there to kind of represent like, oh, that's the y-axis. And you could even do this here. And this is representing the new x-axis that you would get from that translation. That's really what it's called. It's a translation. So if you want to put those dashes there, that's kind of an indicator of the change. Nothing changes on the graph per se. It's still an exponential growth. It just moved to a 3 to the actually it would be 3 to the right, 2 up. Hold on. Oops. So it's going to be 2. Sorry, my apologies. I did that wrong. It's 3 to the right, and it's 2 up. So this is my new y-axis, and this is my new x-axis, and so my graph would look something kind of like this. My apologies, I did it wrong. Glad I can make the fix now, but yeah, that's what it is. Finally, what we have here, we have an exponential graph. It says the graph represents a bacterial population y after x days. They want us to write an exponential function that represents the population. So for instance, the one thing you want to do is, does it have the y-intercept? And it does. It does. 0, 3. This is my value of a. So using y is equal to a times it by b raised to the x power, I know that a is 3. So I got y is equal to 3 times it by b raised to the x power. So now, in order to find b, what we get to do is we get to look at, hopefully they give, in this case, we look at one of the coordinates that's not the y-intercept. So here, this is x, and this is y. So we can say that to find b, I can say, oh, this is 12 is equal to 3 times it by b raised to the first power. Well, I can divide 3 to both sides. So now 4 is equal to b. So my equation for this particular exponential function is going to become y is equal to 3 times it by 4, excuse me, raised to the x power. Because I found a right here. I found b from here. The second question is they wanted you to find the population after 12 hours and after 5 days. So 12 hours is half a day. So for the first one, you're going to say that y is going to be equal to 3 times by 4, and then x is going to be raised to the 1/2 power, because that's half a day. And then the second one is going to be y is equal to 3 times by 4 raised to the 5th power. So looking at the first one, 4 to the 1/2 is 2. 2 times 3 is 6. So I get, my answer is 6. It must be the bacterial population. And then for 5 days, it's going to be 3 to the 5th power times it by 3, which is 3,072. So that's population after 5 days, after 12 hours. And that is being able to look at exponential functions. Hope this helps. Till next time.